Welcome back to Tech Talk. On today's episode, we have Kolyn Marshall, and he's going to help with some insight on our Snowmelt systems that I, as a degreed engineer, will be the first to admit I know nothing about. So Kolyn, welcome to Tech Talk.
Awesome. Glad to be here, Todd.
Absolutely. What are some of the challenges that engineers may face when they're taking a look at specifying a snowmelt system?
Well, you know, one of the things that I tend to describe snowmelting as, it's the art of the best guess.
Art of the best guess, okay.
Because you just don't know. Engineers like defined parameters. You know, you're looking at a house, if you're doing the heat loss, the house is fixed. It's always going to be that house. It's an R13 wall. It's 12 feet of glass. It's all these things are going to be fixed, and that's easier to work with. Snowmelt systems are less consistent, and the biggest driving factor there is how much snow am I melting? Mm-hmm. You know, and I'm sure you see it up here as everybody else does. We design for maybe a 12-inch snowfall.
Okay.
But how often does it snow 12 inches?
Okay.
You know, the first snow of the year may be 6, and then later on it's 12, and you may get a big one that's 24.
Okay.
And you can't constantly go out and start changing your system once it's installed.
Okay.
So as a designer, we want to try and capture that environment as best as we can. And so those are some of the factors that we play with. Right.
So with those variations and those factors, like you said, 6 inches versus 12 inches versus 2 foot or whatever, what are some of the impacts, or what are some of the things that you'll consider, that you'll see? How does that impact the design of a snowmelt system? Would you have to wait a little longer as opposed to?
Exactly.
Okay.
Exactly. So the main thing that happens is that time is the factor that becomes the variable.
Okay.
Right. So if I design for a 12-inch snowfall and it says I need 150 BTUs a square foot from the design reports and 120-degree water, great. If it's only a 6-inch snowfall, then what will happen is it technically is less BTUs, which means I just melt faster.
Gotcha.
Right? Because I'm a little bit oversized. Now, if it goes the other way, if it is suddenly an 18 or a 24-inch snowfall, I'm still stuck with that 150 BTUs a square foot design that I had initially.
Right.
It may need a little bit more, but what we're trying to say is that you need more BTUs to melt it in the same amount of time.
Gotcha. Because
I don't have the BTUs, it's my time factor that gets extended. So instead of melting inside of 3 hours, let's say, it melts inside of 4 hours. The time factor is all over the place for every snowfall.
Okay.
It'll be a little bit quicker, it'll be a little bit slower. It's going to be within a window. Usually within 3 to 4 hours, you're going to see melting, right? And the truth is, as long as it melts, nobody cares.
Gotcha.
Right? If it takes a little bit longer, an extra 30 minutes or an hour, that's really not the factor. It's the factor is, did it melt?
Right.
Yes, it did.
Right.
And that's what everybody's looking for.
Gotcha.
Right?
Gotcha. What are some of the parameters, or what are some of the things in the design of a snowmelt system that are major factors in the success, or what you need to consider?
That's a great question. Obviously, the layout as far as the area to be melted, right? So physically, we're looking at the geometry of the space.
Okay.
How long, how wide, what's the square footage? So the square footage is going to tell me basically how much pipe I need.
Okay.
Right. So if it's 1,000 square feet, I'm going to need, if I go in at 9 inches on center, for example, I'm going to need about 1,400 feet of pipe. Right. So I know how much pipe I need. The dimensions, the length and width, will tell me what the run needs to be, because I need to be able to get from point A to point B and back again with a pipe, a loop of pipe. That's usually going to be the longest distance from corner to corner. And that parameter of length and width will dictate what that shortest run can be.
Okay.
If it gets to be if it's a sidewalk that's really narrow but really long, then I'm dealing with longer runs. And the longer the run, the bigger the diameter of the pipe needs to be. And the game that I'm playing with there is pressure drop. So the bigger the diameter of the pipe, the lower the pressure drop over the run of pipe is.
Okay.
All right. So it's a pump selection
Gotcha.
issue. Can I do it with a smaller diameter pipe? I could.
But
I just got to go with a bigger pump.
Right.
Right. So I'm shifting that load, that burden from one aspect to another, depending upon what I'm trying to do.
Gotcha.
So as an engineer, from a design standpoint, I want to optimize as much as I can, from the snowmelt performance to the mechanical requirements. Okay. So I have that factor that I'm looking for. The other thing that I'm looking for is, how am I going to break the area up? Right? You know, if I have a parking lot and a sidewalk next to a building, I might be able to do it all together, right? So common thought practice is if it snows in the parking lot, odds are it's snowing on the sidewalk.
You would think.
You would think.
Expect.
And we would want to group those together. Makes sense. Simplify the mechanics, simplify the controls. Great. One thing we tend to forget about is the sidewalk next to the building
Okay.
is going to have a different environment, ironically. It's going to be buffeted by the building itself. It can be wind trap, so you get more blowing snow. You could have secondary snow accumulation because things sliding off of roofs, right? And you have snow pileup for that. It could be just solar gain. So we don't realize how much the sun attributes to melting the snow and preventing things from icing over.
Right.
It snows and the next day it's nice and sunny and the areas in the sun are going to melt first. And if you're by a building, that sidewalk may actually be in shadow most of the time and doesn't get that benefit of additional melting.
Gotcha.
So you may need to break those areas out to allow for additional control options by the building.
So it's interesting, like you were talking about the art of the best guess, or
Right.
engineering guess, however you put it, where your pump size could be determined by your hose diameter, or your hose diameter could be determined by your pump size. All right, so there's the best guessing there. But I think you also illustrated that there are some of those strategy design elements in terms of how you break up, how you consider the environment, or even like you're talking about, where does the water go?
Right. No, exactly. So some of the factors that we use to anticipate performance will be what we call a free area ratio.
Okay.
And what that applies to is how well do I want to keep up with the snow melting as the snow falls? Like a free area of 0 is basically going to allow the area to accumulate fully with snow before it really starts to melt. It's the longest response time, slower to get to melting. That could be light residential. Maybe it's a secondary location, so maybe it's a vacation home, and you're not there all the time. Well, you don't need it to be real responsive. The second factor is a free area ratio of a 0.5.
Okay.
And so it's going to keep up with half. So as it snow is falling, we're going to keep up with half of the snowfall and melting. And then a 1 is going to be a full melt. So as the snow is falling, it's melting. It allows for no accumulation.
Gotcha.
That's going to be more of your emergency access ramps, your hospital entrances,
Airports,
helipads, that sort of thing. Then you start looking at percent of occurrence. And so I'm designing for, take our example before of 12 inches of snowfall. How likely is it to be 12 inches of snowfall? If my confidence factor is high that it's always going to be 12 inches, then I design around 100%,
Right.
and I'm going to always deliver that potential.
Right.
If I think it's like, it's a little bit less, or I'm kind of not sure, I can design around a 95% confidence level or a 90% confidence level, and my loads will start to shift because I'm guessing, I'm taking the chance that that 12-inch snowfall is going to be the exception, not the rule.
Gotcha.
And so my loads will be a little bit less.
Gotcha.
And so I'm just accepting the fact that when I do get to design, I have a longer lead time.
Right.
So I'm just playing with the numbers
Gotcha.
at that point. You mentioned water runoff. Got to account for it. Water's going somewhere.
It's got to go somewhere.
Melting snow.
Exactly. Snowmelt system.
Snowmelt systems.
Who'da
And
thunk?
so now the water's going to go and go to the lowest point, and that's where a drain needs to be. It could be a trench drain. It could be any number of things. We just have to account for the removal of that water.
Gotcha.
In the summer, when we're dealing with rains, water's going everywhere. So it can flow to the sides of the concrete pad, down the slope, anywhere, right? And the ground next to it is thawed. And so the ground is going to absorb some of that water.
Okay.
In a snowmelt scenario, you don't have that. The ground could be frozen outside of the snowmelt pad.
Right.
And you actually have snow that's on the ground. So
Right.
you get the chute effect. And it will actually funnel water down to the lowest point. And so you actually end up with more water present potentially in a snowmelt system than you would if you had an inch of rain during summer.
Right. Gotcha.
So it seems or can be amplified in the volume of water.
So with everything that you just explained, and going back to a statement that I made before, maybe there is an element of rocket science to
A
this.
little bit. There's a little bit. Yeah.
So how would someone approach you, an engineer, a specifier approach you to get started on their Snowmelt system?
We do offer free design assistance from Watts. We have an email address. It's designs with an S at watts.com. And just send in a request, attach drawings of the Snowmelt area in question, and we'll take a look at it and let you know what's required.
Is there anything else that you could think of that someone would need to know that's pertinent to a Snowmelt design system?
Oh, there's a lot. There's a lot. I don't know if we have time.
We may not have time.
We may not have time. There's a lot of opportunities with the Snowmelt system. And it ranges from, you can use concrete for the Snowmelt area to sand and brick pavers to asphalt. So there's a lot of different materials that we use today in construction. Snowmelt's compatible with. There's a lot of heat sources that are great sources to provide energy to drive the Snowmelt system. It can be traditional boilers. It can be waste heat from a manufacturing process. It can be waste heat from a freezer or a cooling system. There's a lot of areas where we can optimize efficiencies and really get a system that can almost be zero cost to operate. And provide a much safer environment for people using the space. So there's a lot of things that we can look at, a lot of ways that we can value engineer a system to be the most effective that we can.
I feel smarter already.
Well, that's good. That's
Outstanding. Colin,
mission accomplished.
Thank you. Absolutely.
Awesome.
Appreciate your time.
Anytime.
Appreciate your time. We'll see you next time on Tech Talk.